All right, so we've established sort of our foundation for talking about forces, fields, potential energy, and potential by what we've been talking about so far in the class with gravitational forms of all those things. Now we're going to transition and start talking about electric. So we'll end up talking about electric forces, electric fields, electric potential energy, and electric potential. To set all that up, let's start by just talking about the very basics of electric charge. So electric charges have the following properties. For one, unlike charges attract one another, like charges repel one another. Which means if we've got a situation like this, you see here we've got something that I've just denoted as, hey, this charge is colored red, this charge is colored blue. These are opposite, they're attractive, or they're attracted together, whereas you put two red charges together, they're going to repel. You put two blue charges together, they're going to repel. So part of what you end up seeing is that, well, we just give these things labels. The red charges we call positive charge, in this case. The negative charges, or the blue charges, we call negative. So one of the things that's very interesting is that when we talk about mass, we only have positive mass because the gravitational force is always attractive. But the electric force can be both attractive and repulsive. So we need two types of charge, which is why we have positive charge and negative charge. Now, in addition, electric charge is always conserved. So particularly when we talk in terms in circuits, what we'll see is that when we talk about charges leaving or charges entering, those charges have to come from somewhere, right? So electric charge is always going to be conserved. And then charge also comes in discrete packets. Now, if you're talking about a large amount of charge, and when we talk about 1 coulomb, so coulomb, capital C here is our unit for charge. 1 coulomb is a tremendous amount of charge. And so we wouldn't, as a general rule, talk about 1 coulomb in terms of the number of electrons, but the fundamental unit of charge happens to have this value. So E is 1.602 times 10 to the minus 19th coulombs. You can't break charge up into smaller values than that, at least not without going into subatomic structure. So the electric charge E here, again, E is a positive value. And so what we're going to say is that a proton carries a positive E worth of charge. An electron carries a negative E worth of charge, and putting the two of them together gives us a neutral atom. So to talk about a neutral atom means, as a general rule, a neutral atom doesn't mean that I have zero charge. What it means is that I have as many positive charges as negative charges. So this would be, in this simple example where I've got 1 proton, 1 electron, this is going to be neutral hydrogen. And that's just saying I've got as much positive charge as negative charge. If I add a second negative charge, then I have a negatively charged atom. So again, sort of these two, the ones that I started with, cancel out, but I've got this one left over. So something being negatively charged is a way of saying that it has an excess number of electrons. If something is positively charged, well, that's sort of the opposite case. So here, something is positively charged because I've taken away the electron that it started with. So as a general rule, what this means is that things that are positively charged are positively charged not because we've added positive charges, but because we've actually removed the negatively charged electrons, and so you're left with sort of a deficit of negative charge in a positively charged material. Now, speaking of materials, there are two types of materials. One's a conductor. And a conductor is a place where the charges move freely in response to an electric field, and the charges, again, are the electrons here. So typically with a metal, what you have is that for most metals, the electrons are in some sense very loosely attached to the metallic structure, and so they can sort of go from atom to atom, and that's why they're able to sort of move within the metal, and the metal serves as a good conductor. An insulator, the opposite's true. So for insulators, those electrons can't move freely in response to an electric field, and so what you what you end up with in an insulator is you put an insulator in an electric field and it polarizes the material, but those charges can't get away to flow freely. So in the same way that the conductors we tend to think of metals, insulators are the things that plastic, wood, glass, rubber, right? Things that you're not worried about picking up a shock off of. So with our conductor, what you'll see is, again, what I've done is, so I've charged this rod positively, which again means that what I did was I rubbed off negative electrons and left it with a net positive charge. And then as I bring it near to a conductor, what's going to happen is that basically these electrons can flow over here to be close to the positive charge, and so it's going to leave those electrons free to move about the material. But with my insulator, they can't. So they can't get away, which means what they end up doing is polarizing the material so that on sort of the atomic scale, they set up this electric field or react to this electric field by the negative charges do move closer, the positive charges do move away from my positively charged rod, but they just can't flow freely around the material within my insulator. Now there are two ways that I can charge a conductor. One is called charging by conduction. And so as I'm charging by conduction, basically what I'm doing is I'm going to bring my rod up close. Again, I'll see that my charges move freely in response to that rod. When I go ahead and touch my charged rod to my neutral conductor, some of those excess charges are going to move off the conductor onto the rod, and so what that's going to do when I separate them away again is it's going to leave me with less of a charge on my original neutral rod, but now a positively charged sphere. So basically I took some of the electrons away, they've redistributed themselves over both of these devices, which is this one less positively charged, but now what was my neutral conductor is now also positively charged. So this is charged by conduction. Again, I need contact for conduction. The other option I've got is called charge by induction. And so I'll start the same way, but in this case, instead of touching my rod to my conductor, what I'm now going to do is again set up my same scenario where I've got my charges moving freely in response to it. So this time what we're going to do is we're actually going to attach a ground to the far side. So this symbol where you see sort of a series of lines that get smaller as you go away, that's the schematic representation for a ground. And what a ground does is it basically provides a source for electrons if you want them, or a place for electrons to go if you don't. And so here, what's going to happen is that our ground is going to see this positively charged side, and it's going to basically draw electrons up onto the sphere. And so what we're going to be left with then is a negatively charged conductor. So the charges, these excess electrons that we pulled up through the ground, those are going to be left on the sphere. And so when we remove away our positively charged rod, it's still charged as much as it was before. And now we've got the negative charges that we've drawn up from the ground.